Hi everyone, I'm recording this video to show you the solutions to homework 2 and I guess this video may get too long, so I probably will do 2 videos instead of 1. Okay, so let's get started. The first question is we want to do a sequential search, and a sequential search means say if we have an array and then this array of several items, and then let's say we have 5, etc. So if we are looking for example, 2, and then how do we do that? And the easy way is, how about we just visit all the members one by one, right? So we visit first member, it is 0. Visit second member, it is 0. So we keep on doing the visits and until we find the value we are looking for. But for this question, I'm asking for a index. Okay, so we are returning an index. So this means when we are visiting the values, it's better that we have the indexes ready. Okay, so this is my idea. I want to do the one-based indexing from 1 to the length. So for each round, I'm going to use this I as the index. Well, and I'm doing something similar to our textbook, so I'm doing one-based indexing instead of zero-based indexing. But for your pseudocode, either way is fine. Okay, and then for every round, I want to use the I to grab a value, and I want to check whether the value on index I is the value I'm looking for. And then if it is, I'm returning the I. So in this way, this will give me the control of the I, so I can, when I find a value, I can immediately return the corresponding index. Okay, so this is for the first question. And for the second one, we are doing a binary search. So for a binary search, the idea will be different. Well, and for example, this is the array that, so I'm drawing this rectangle and say, okay, this is the array that I want to look for a certain value. And then another information I know is, well, for all the values, they are pre-sorted already. Wait. Okay, so if we are visiting a certain value, and then, well, we want to if we're searching for a certain value, we want to go to the middle. So the middle one, for example, is here. So this one is the value in the middle. And then if you're lucky, the value in the middle is indeed the value we are looking for. And then we return the middle index and then we finish. And otherwise, well, and then we need to make a decision that are we looking for the value in the lower half or the value in the upper half. So for example, we know an array is sorted from low to high. And then when we are touching the value in the middle, we find, for example, here there is a 15. Okay, and then remember we have this array from low to high. Then if we are looking for 20, and then what do? You know the middle value is 15, but we are looking for 20. And then in this case, you only search the upper half, which is this part, and then you don't want to search the lower half again, right? So this is the idea for a binary search. And for the binary search, there is a condition, precondition, that we have to have the list pre-sorted already. Okay, so let's take a look on how I would implement this. So at the very beginning, I'm going to assume that I have 2 cursors, a left cursor and the right cursor, and they are started from both sides. And then, as long as the left cursor is still smaller or equal to the right cursor, and this means there is still a valid search space for me to do the search. And then I'm going to go and try to grab the middle index. So the middle index will be this one. And then once I have the middle index, and then I want to use the middle index to grab the value, and in this case it is 15. And if this 15 is indeed the value I'm looking for, and I'm lucky, and then I'm going to return the middle index because that is the index that I can find a 15. But say if I'm looking for say I'm looking for 10, for example, and if I'm looking for 10, and then I'm going to search the lower half. And so how do I redefine the search space so that it searches only the lower half? And this is what I would do. So I'm gonna keep the left cursor the same, but for the right cursor I want to move it one lower the middle index. So we have the left cursor here and the right cursor here. And this is the search space for now. Because I'm looking for 10, this 10 is lower than 15, so I'm only going to look for 10 in the lower half. So this is going to be my strategy. And then if you're looking for 20, for example, and then I'm going to do something just the opposite. So I'm going to keep the right cursor where it was. So the right cursor will stay here. And then for the left cursor, I'm going to move it one above the middle. So in this case, this will guarantee that the next round I do the search, I only do the search in the upper half. Okay, so here are a few other questions. Explain the exit condition of your solution. So there are two possible ways that we stop this search. The number one is, well, in a certain round, we find a middle value. And then this middle value is indeed the value I'm looking for, and then I'm going to stop. And then the second part is, remember, as long as left is still smaller or equal to right, and then I'm going to keep on doing this search. So this means as we make the search space smaller and smaller and smaller, and there will be a case that the right cursor is no longer on the right side of the left cursor. And what does that mean? The right cursor is even lower than the left cursor. This means the search space is no longer valid. And this means, well, we have exhausted all the possible ranges that we can find this value, but eventually we can say we don't have such a value. Okay, and the next question is, well, explain why or why not binary search algorithm always find the first occurrence of such a value, and the answer is no. And then how do I explain that? I can give you a really small example. Say I have a string of 5, 5, 5. Okay, so this is just a list of 3 5s. And then I'm trying to do a binary search. I'm looking for a 5. And it will return the first 5 I find. So in this case, which will be the 5 to be returned? Or which is the index to be returned? And the answer will be, well, at the beginning, we are going to have the left cursor and the right cursor here. So the left cursor and the right cursor. But if we are looking for the middle, we are going to have the middle one. So the middle one is indeed a 5. So following my algorithm, if, well, we are having the middle one is exactly the value we are looking for, we are going to return the index of the middle value. And in this case, I'm going to return the index of the middle 5. So this means it's not guaranteed that if we are doing a binary search, it will always give us the first occurrence of 5. Because in this case, it gives me the second occurrence of the 5. Okay? So the next question, I'm going to get rid of everything here. The next question, binary search. So for a it's bubble sort. And for the bubble sort, what we are doing is we want to analyze the TN, and then from the TN we want to figure out the big zeta. And then how do I attack this problem? So if I want to copy, okay. So if you want to copy the code here, and then I'm gonna just try to figure out. Okay, so I think this question mark is kind of annoying. I'm gonna erase a question mark because it is really a in here. So for I in 1 to the length, and for j in length down to I. Okay, so I'm gonna just fix it a little bit, and then I'm gonna try to visit each of the line and then try to figure out how many runs will the code be executed. Okay, so the first line is kind of easy because, well, if we assume that there are n values in such an array, and then I'm going from I to the length, so this means from the beginning to the end. So it will run for n runs. So this one is easy. And the second line is kind of hard because, well, how many runs the line 2 is going to be executed depends on what is the I value. and say for the first round, I is 1, right? So when I is 1, it is from n down to 2. So in the first round, when I is a 1, and then it is a n down to 2, so it is n minus 1 rounds of the execution when I is a 1. And the next round, when I increases to 2, and then the number of the rounds that the line 2 will be executed will be from n down to 3. So it will be n minus 2 rounds. So it will be keep on adding that, and eventually we're going to do plus 1 and then plus 0. Okay, so this is how many rounds how many times that the line 2 is going to be executed. So this is kind of a number that we are going to use a summation to add them together. Okay, and then how about line 3? So my observation is every time we enter the line 2, we enter the inner loop, we are going to do line 3 guaranteed. So this means, well, I'm going to just copy this part, and then the number of the rounds that line 3 is going to be executed will be exactly the same to the number of the rounds that line 2 is executed. But for line 4, the story is different. Well, the condition is always going to be checked on line 3. But if we are lucky, what we can have is, say, there 1, 2, 3, 4, 5. Okay, so in this case, well, we want to check the value pairs. And for each of the value pairs we check on line 3, and we are lucky because we don't have to do any swaps. So this means for line 3, it will give me false all the times. And in this case, and we will never touch line 4. So line 4, the best case is, well, it will never be triggered and we don't have to run line 4 at all. But what is the worst case? So in the worst case, it might be possible that for every pair of the values we check, they are in the wrong order, so we want to do a swap, and then we check the next pair, we have to do a swap again. So this means, well, in the worst case, we are going to execute the line 4 the same times we are going to execute line 3. So that is the worst case. So, well, this answers the first part. What is the worst case and what's the best case? So the worst case is every time we check a pair of the values, we have to do a swap. And the best case is every time we check a pair of value and then they're in the right order already, and I don't need to do a swap. So that's the best and the worst. Okay, so to answer the next question, what's the worst case? So for the worst case, we are going to add this part, this part, this part, and this part together. So we add all those 4 parts together, and then if you use summation correctly, you will have the Tn as this part. And then how about the best case? So for the best case, we are going to do the line 1, line 2, line 3. And remember, for the line 4, it will be a 0. So this means we won't touch line 4 at all. So if you just add all those 4 values, and then you are going to have the Tn as n squared. Okay, so that is the Tn for the best case and the worst case. And the next part will be, well, after you have the Tn, and this is a polynomial of n already. And after that, you have to find a lower bound and the upper bound. So for the worst case, and this is the Tn I have, and then I can say, so for this Tn, it will always be smaller or equal to 2n squared. So, and remember, how do we define the upper bound? So upper bound means, well, we want to find a CFN so that, let me make it larger, so that for all the n greater than n0, and then this CFN is always greater or equal to Tn, right? So this is an upper bound. So if we have Tn as a curve, and then we want to find a constant C multiplied by Fn, and then Cfn is always going to be greater or higher than Tn after a certain point of n0. So if I want to draw this kind of curve, and what we are looking for is, say, like this, like this. say, well, for this one, this might be a curve like this. And then I want to find, this is a curve for the Tn, by the way. And then we want to find another curve which is always higher than Tn after a certain value. So for example, I can draw this curve like this. So this curve is going to be n, it should be 2 n power 2. Okay, so in this case, well, if I say the curve 2n squared is always higher than Tn, and what is the c? So c is going to be a 2. Okay, and what is Fn? Fn is going to be a polynomial of n, and then in this case, it is n squared. Oops. And then what is the n0? I do have to specify a n0. So in this case, I'm just going to say, okay, after 2, for example, and then the new curve is always going to be higher than the Tn curve. So in this case, this n0 is going to be a 2. Okay, so after doing so, and then I have already found a CFN that after when n is higher than n0, and then, well, CFN is always higher than Tn. So this proves that this Tn is O n squared. Okay, so this only touched the O n squared part. And after that, you also want to find a lower bound. So for the lower bound, and I see this is a 1.2 n squared. So if I want to make the most significant part grows slower, I can choose to do a 1 n squared instead of 1.5 n squared. So in this way, well, after a certain point, I can prove. So 1.5 n squared minus 0.5 n is gonna be greater than 1 n squared. So I want to find a lower bound, probably somewhere here. So this is going to be a curve of n squared. So after I find that, so this is a upper bound, this is a lower bound. And for the upper bound and the lower bound, we are able to prove that for this Tn, it is both O n squared and omega n squared. So once I have the upper bound and the lower bound, and they are both n squared, eventually I can claim this is theta n squared. Okay, so this is only for the worst case. And then for the best case, you gotta do something similar. You have to find the c, the fn, and the n0 to show me it is O n squared. You also want to find another set of the c, f, n, and then n0 to show me it is omega n squared. So after you have the information, it is both a O n squared and omega n squared. Put them together, and you can prove it is theta n squared. Okay, so I guess this video is long enough already, and I will continue in the next video. Bye bye.